Greetings. Welcome to DC Circuits. This is your first course or should be your first course in the study of electricity and electronics and circuitry. It's the beginning of a wonderful career. A couple of topics to get out of the way. We will have our first labs on Monday, August 24th, 7:30. Just meet in the lab room in the building. We will disperse as we need to. Make sure you're masked and you come in the correct way. I will have to split the class up into a couple of rooms, but we should be able to handle it from there. Make sure you got the syllabus. I will have to update the COVID-19 form. I just found out this morning myself that there's another form that we need to use instead of the one I put up there. So as soon as I get that form, I'll update that on there for you to sign and return to me. Also, make sure you sign up for the Remind, and because I will send notices out, things like that through Remind, and that's about it. Okay, let's move on with the presentation. This is our first chapter in the book by Groves. Hopefully you did not buy the big book, the big thick one. We do not need that. You do not need that. You only need the workbook, which is what we'll work out of. There will be homework assigned out of that workbook. We are looking at the 13th edition. I have the page numbers and the problem sets on the syllabus are based on the 13th edition. If we wind up not having the 13th edition, we'll figure that out and move on. For this first lesson, we're going to cover basic electricity and some of the ideas involved with that. You can read them here based on what we're talking about. I'll skim over things that don't really pertain to what we need to worry about for what we're doing. But we will figure most of it out and talk about the things that do matter to us. Okay? Again, I'm not going to read everything on the page. All matter is made up of atoms. And atoms are made up of electrons, protons, and neutrons, even though this particular slide set doesn't mention the neutrons. Protons are positively charged particles. Electrons are negatively charged particles. Neutrons make up the core of the atom, the planet, you might say, whereas the electrons float in a cloud in orbit around the atom, around the core. The neutrons are part of the core to help balance out the electrons floating around in the cloud, in the orbit. It makes a little more sense when you start studying it a little more, but we're not going to get too in-depth with it. The only thing we need to worry about is we're going to worry about those pesky electrons at this point. Boom, boom, boom. Everybody's seen a battery. They all have negative and positive poles, and that's basically what we're talking about. When we talk about electricity, we talk about electron flow, and that's the flow of electrons. Electrons are protons in the atom, blah, blah, blah. Here's a hydrogen atom, and an example, you have one proton in the nucleus, and you have one electron in orbit. Now, this is the Bohr, B-O-H-R, model of atoms. It's the one that's been accepted and used for centuries now, for a century now. We talk about the orbital rings, things like this. I'm not going to get into this. Look at it, study it. Not necessarily study it, but read it and understand what it talks about. We are really only concerned about the outer ring of the electrons, this ring here. Because that, if there are free, like that's an 8-electron orbit, and if there are free electrons, like in this case, this is a carbon atom, there's only 4 there, that means it is available to accept electrons or eliminate or pass on electrons, and so it'll make it usable for, I hesitate to use the word because we haven't learned about it yet, conductors to pass electricity. Same thing with the copper atom. We've got only 1 electron available in an 8-electron orbit. So that's the presence of that holes, the lack of electrons and the free electrons in that outer orbit is what allows atoms to conduct electricity. And matter that is made up of those items are called conductors. Examples of that are silver, copper, and aluminum. 90% of the time we're going to be dealing with copper wire. Some of the older houses around will have aluminum wire in it. And when I say older, I mean like early 1900s, 1920s, that era. Hopefully nobody has any silver wiring because that'd be expensive. And they use a lot of gold in some wires, but that gets really expensive. But when you're talking about something that's vital, like space shuttles, space station, they'll use some gold conductors. Now, the opposite of a conductor is going to be an insulator. That outer band is full, or is close to being full. It doesn't readily accept electrons. An example of an insulator is glass, plastic, and rubber. At some point, if you're working in industrial electronics, you're going to work with have a set of insulated gloves, rubber gloves. That makes it easier for you to work without bothering getting shocked. And believe me, we only work with low voltage levels in what we deal with here, but low voltage does not mean you can't get shocked, you can't get hurt. I was put on my rear by a set of batteries on a bus, and they're only 12 volts. But there were 6 of them, 12 volts, wired in series, and that means I got all the current from all 6 of those batteries at one time. Bam! It threw me across the room. So yes, it can hurt, and if you're not careful, you could get really hurt. Okay, semiconductors, don't worry about those right now so much. Just know that they exist. A semiconductor is sometimes under the right conditions it will conduct electricity. Other times it won't. Carbon is one of those. Silicon and germanium are the 2 big ones that we worry about. You'll learn more about semiconductors if and when you take the semiconductor class, which is 2 classes down the road. This class quartet for electronics guys is DC, AC circuits, then semiconductors, where you get into diodes, transistors, and things like that, and then circuits, which is the more advanced of what we deal with. Now, we talked about the structure of the atom. Read through this. That's great. The thing that we need to learn out of this is we define a coulomb. That is coulomb as equal to 6.25 times 10 to the 18th electrons. That's 10 at 6.25 with 16 zeros after it. And I say 16 because the 18 is 18 places after the decimal place, so it would be passed here. The symbol for electronic charge is Q for quantity. So I don't understand why they come up with that. Don't worry about this, other than to understand that opposite charges attract and like charges repel. Everybody's seen that when they've tried playing with magnets. They've tried playing with 2 magnets and try and push them together at the same poles. They don't mate together, and they don't like going together. We get into a charge to an electron, blah blah blah. Don't worry about this so awful much. If you ever get past what we go through here, it becomes important. But for what we're talking about here, no, it's not. Let that matter. It doesn't matter all that much. Voltage, or the volt, is potential difference. But think of it as potential energy available. It's a force that's going to push current out of the battery. In this case, it has been defined as 1 joule per coulomb. 1 coulomb, or rather 1 joule per 1 coulomb is 1 volt. And in terms of a 9-volt battery, that's 9 joules per coulomb. Okay, what's a joule? A joule is a measure of work, blah, 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 from there. Again, don't worry about it. This is a basic definition of voltage. We'll get to a better one a little bit later. And that really boils down to, notice the difference here. That's still 2, that's 2, and that's 2. That's the same potential difference across all 3. They're equivalent. But it's because I have 1 coulomb here and 3 here, 0 coulombs, 2 here, blah, blah, blah. Okay. The difference is, and that's what generates a charge. When you get electrons flowing, current is a continuous flow of electrical charges such as electrons. And that's basically just these things flowing through here like that. The amount of current is dependent on that, the amount of the voltage applied, and we'll get into that because that is an immutable law that we get into called Ohm's law. We'll find out more about that later. The unit of measure for that is an ampere. Now I'll get into that a little bit more. We use this letter I. I don't know where they come up with that, so I for intensity bit. But we always use the letter. One of the first passive components that we worry about is a resistor, and that is the resistance is the flow, the opposition to the flow. It means I don't want it to flow, so it's preventing it from flowing some. And that generates heat, that generates a few other things. Excuse me. The unit of resistance is an ohm, and it's represented by omega symbol. And we use R in schematics to represent resistance. Now, if you get a chance, you need to look at these pages. The voltage of potential change for charge to move. It has a unit of volts. It's named after Alessandro Volta. Resistance is ohms, named after Georg Ohm. And amperes, for the current, is named after Andre Marie Ampere. Read their biographies. Learn a little bit about where these come from and why we name these basic units after them. Resistance is the opposition to current flow. It's that simple. Here, this is a resistor. One looks like. We'll look at some more in the next lesson. Here's the schematic symbol. Although you see, if I draw it, it won't be quite that neat. I tend to get in a little hurry. And we use R to represent resistance. Now let's put them all together. When you put them all together, you get a circuit. And we start with these three components simply because we have to have all three of these to be present to have a circuit, complete circuit. There has to be a voltage source. We have to have current flow or a path for the current. And there has to have some kind of resistance or a load. We'll call that a load down the road. An open circuit is when something's broken, you have an incomplete circuit. If you can put a meter on it, you measure it, it has an infinitely high resistance. It'll just tell you it's an open circuit. If you have a closed circuit, or a short circuit, that means something is being bypassed and allowing the current to flow in a path that you haven't defined or that's not part of the circuit. And it could be your body, so you have to be careful about that. You may not feel it, but it could be still going through your body. Current will always go through the path of least resistance. Always go through the path of least resistance. Remember that. If your body has less resistance than the circuit you're measuring and you put your fingers across it to try and measure it, you could be affecting the reading by it reading you as opposed to what you're trying to read. Here's an example of a complete circuit, closed circuit, current's flowing. Here's the schematic. There's a schematic for a battery. Here's a schematic for a resistor. If I had current would be flowing like this or like this. We'll get into that in a minute. Here's an open circuit. And a short circuit would be something like it's like a wire is attached there. So it's going to go through that wire because it doesn't like the resistance. So it's going to bypass that resistance. Now here's where I'm talking about with the current flow. I grew up in my career learning about current flow as the electrons flowed out of the positive side of the battery, went through all the circuits and came back in the negative side of the battery or went to ground. We call that conventional current flow. Well, lo and behold, we did a lot of studies, a lot of work, and come to find out that it really doesn't. The electrons really don't come out of the positive pole of the battery. They come out of that negative pole. So, coming out of the negative pole, going through the circuit, we call that electron flow. Now, for our purposes, it really doesn't matter all that much because the math works out the same. the math is still going to be the same. The circuit's going to be solved the same way, so depending on which way you look at it is up to you and how you deal with it. Here's an example of that. The thing I would ask that you do is, when looking at this, make note of your polarity, your voltage source, because that's going to affect it. Here's an example of electron flow, positive, negative, and positive and negative. Here's an example of conventional flow. This is generally the way I will draw them and work with our problems as we go through. A couple of more slides and we'll be done. DC current is direct current, flows in only one direction. Alternating current is AC, and it periodically reverses direction. And that period is the frequency of the AC, which we'll get more when you get into the AC components. I like at this point to point everybody towards a great movie called The Current Wars, Current, and it starred Benedict Cumberbatch. It is about, Cumberbatch played Edison. I can't remember the other guys in it, but it's primarily about Nikola Tesla and Edison and Westinghouse. It's a fascinating story. We are eternally grateful to Nikola Tesla for alternating current. DC current Edison was a proponent of DC. Westinghouse is a proponent of AC. Actually, Westinghouse is a proponent of anything opposite of what Edison wanted. Tesla codified the mathematics for AC. AC was around long before him, but he codified the mathematics and he developed a generator that was efficient enough to be used in alternating current. He came across from Hungary. He didn't come across Hungary. He came from Hungary to the U.S. and managed to apprentice himself to Edison. Edison made big promises if he would fix all of his stuff. Well, he fixed all of his stuff. Edison didn't follow through on the promises. He just basically used him, threw him out the window. And Tesla left. He started out on his own, building some of his inventions. Westinghouse wanted to bring him into the fold. I can go further and further from there. It's a fascinating story and a fascinating study. Watch the movie The Current Wars. I think it's on Netflix now, I'm not sure. But it's a fascinating movie, and it gets it mostly right. Enough to where you understand what's happening with it. Here's how a DC voltage looks on a graph or on a scope. Here's what an AC voltage would look like. It's sinusoidal in shape. There are other shapes, there are other forms, but we primarily worry ourselves, ours is primarily sinusoidal in form. Blah, blah, blah. This is where it comes from, blah, blah. Multimeter is your friend. We will talk about it more when we get in the lab because you will be using them the first day. And that is it for this. Again, speaking of the first lab, Monday morning, August 24th, 7:30 in the lab. Be there. Make sure you have your lab kit with all your parts. You have to have that. You'll use that lab kit for the next 4 years. Or next 4 classes, rather, not 4 years. Next 4 classes. So make sure you get it. It would help if you would organize it at some point. You'll know more how to organize it a little bit later once we get going. Thank you. Have a good day.